video is going to be an introduction to t-tests. We're going to have two different videos on these, and this one will focus on when we have one sample that we're comparing to some type of hypothesized value similar to the chi-squared test, and the next video will be the two-sample t-test. So as we move forward in this particular course and as you move forward in your career, you're going to be acquiring an arsenal of different statistical tests that you can use to determine if we're seeing any type of significant effects based on some type of either internal or external driver. And one of the questions is, well, how do I know which test to use? And this is partly what this class is for you to gain an understanding of which tests are most appropriate based on the situation that you have. And as you get more comfortable and learn more about these tests, the appropriate choice is going to become more apparent. And so far we've got two different tests in our arsenal. We have the z-test, in which we're looking at the probability of a function with a normal distribution and when we know population parameters. And then we also have the chi-square test now from our previous videos, where we're comparing our sample distribution to some type of theoretical distribution. This particular video is going to focus on our ability to compare our sample mean with some type of theoretical value, and in the next video to compare two different means to each other. So the t-test is based on the t-distribution. This is something that we talked about in the distribution lectures. If this is unfamiliar, go back to those lectures, rewatch them, make sure that you feel comfortable. We're going to cover this really briefly here. And so the t-distribution is similar to the normal distribution, in which it's symmetric, it's bell-shaped, but the level of peakness and how much it's spread out is going to vary based on the degrees of freedom. So this is going to be influenced by our sample size, and it'll also be influenced by how much variability we have in our respective data set. And we use the t-distribution to estimate population parameters when we don't know the population variance. So we can't use the standard normal distribution in this particular situation. Now, similar to the chi-square test, there are a variety of assumptions for using the t-tests. These include random sampling, independent measurements, normality of data. These are things that we're pretty familiar with at this point in the semester. And then there's also an assumption of variance. And we're going to talk more about this later because it's going to apply more to the two-sample t-test rather than the single t-test that we're going to talk about in this video. So when we're thinking about the t-test, for all of these statistical tests moving forward, we'll have a null hypothesis, and our null will be that the population mean equals some type of value. This might be based on a published value or something that we feel is appropriate. And we're going to test this using the sample mean, the sample standard deviation, and the sample size. And so having information about the population is not necessary for this particular test, and that's why it's so useful for us. So similar to the chi-square test, we have a test statistic in which we will then use to determine if we should either support or reject our null hypothesis, and that test statistic is t. And so we have our formula here in which t equals the sample mean minus that hypothesized value that we're interested in testing against, divided by the standard error. And as we know with the t-distribution, the distribution is based on the degrees of freedom, and these are going to be based on our sample size minus 1. Now, we've got our null hypothesis. Our alternative hypotheses can take a variety of fashions, as we know. This could be that the mean is greater than that hypothesized value, and so the area under the curve that we're going to be interested in this particular situation is going to be to the right of that value of t. We could also hypothesize alternatively that the mean is less than that particular value that we're interested in. In this case, the area to the left of t is what we would be interested in. And then also we could look at our alternative hypothesis and that the mean just simply does not equal that hypothesized value. And in this particular case, we're interested in both the area to the left of t as well as the area to the right of t. We're going to talk more about this as we get into the examples so we can illustrate the point. But I'd strongly suggest checking out section 9.5.2 in the text for more clarification on this. We'll also talk about this in the lecture. So let's look at an example to see how this t-test works. Let's say that we're interested in spinner dolphins and we're interested in their weight. It's hypothesized that adult males weigh 100 kilograms. And let's say that we take a sample size of some dolphins and we want to determine if their average body weight is different than this, specifically if these dolphins are heavier than 100 kilograms. And this might be based on interest in body reserves. If they're planning to make a migration, we want to make sure that they have enough reserves in their body to make it to their destination, food availability, or maybe overweight. If these animals are too heavy, maybe they're less capable of actually capturing food because of their hydrodynamic capabilities. So we go out, we sample these dolphins, and we get a weight for each one of these respective dolphins, and we want to test the null hypothesis that the mean of the population equals 100 kilograms. Now, for our alternative hypothesis, we can use the context of the word problem or the question to help us decide which alternative hypothesis is most appropriate. In this case, we're interested if the dolphins are heavier than the average of 100 kilograms. So in this case, our alternative hypothesis is going to be that mu is greater than 100 kilograms. So when we think about our potential options for alternative hypotheses, whether they're greater than or less than the hypothesized value, or that it's just simply not equal to the hypothesized value, we need to take into account the question, and this is then going to dictate which part of the distribution that we're interested in. In this particular case, we're interested if mu is greater than that hypothesized value of 100 kilograms, and we would consider this to be a one-tailed test. Now, one-tailed tests are only focused on one side of the curve, as they describe. Now, in practice, we should only be using these one-tailed tests if there's a particular reason to do so. Now, this could be based on the question of interest, or this might just be based on the word problem that you're given in this particular class. Now, the reason for this is that if we're considering both sides of the curve during a two-tailed test, because we're interested in both the right tail and the left tail of the test, of the distribution rather, it makes our determination of whether we're seeing a significant difference from the mean to the hypothesized value more conservative, meaning that it requires a more extreme test statistic. In our case, it's going to be this t-value that we're calculating in order to actually reject the null hypothesis. And this is key for statistics because we want to be conservative to avoid making that type 1 error, rejecting the null hypothesis when in the real world it's actually true. So let's illustrate this with our t-table. Now, this t-table is slightly different than the one that we use to understand the t-distribution. The reason for this is that in the top rows here, we have both a row for one-tailed tests and a row for two-tailed tests. And so this gives us a bit more freedom in which to use one table to address multiple questions. So let's say that we're interested just in our one-tailed test and we're setting a significance level of 0.05. Again, this is going to be our default for this particular class and in general in your career in marine biology. So for a one-tailed test, we would find the appropriate number in this respective column. But for a two-tailed test, we would move to the right one column because of that shift from focusing on one side of the curve to focusing on two sides of the curve. Now, in our particular example, we would then determine what our degrees of freedom are, which are going to be n minus 1. So if we have 6 dolphins that we've taken the weight of, this would be 5. And we can compare the values for the critical value, or the critical test statistic that we need to overcome in order to determine if there is a significant difference and reject that null hypothesis. What you notice is that as we move from left to right on this table, the values get larger. And so in order to exceed that critical value, our test statistic actually needs to be larger when we have a two-tailed test versus we have a one-tailed test. And so the difference between our sample mean and that hypothesized value needs to be larger. The actual mean of our data needs to be bigger in order for us to discern some type of a difference, even if we have the same data. And when we're comparing just a one-tailed test to a two-tailed test, we see these differences. And so when we are going through these examples, it's going to be important for you to understand when we're choosing a one-tailed test versus a two-tailed test. And as you're going through practice problems and we're working on this in class, it's going to be critical for you to identify whether we have a one-tailed test or a two-tailed test, because this is going to dictate your critical value and potentially your inference about the population. So let's go back to our example here. We've got our 6 dolphins. We can use our formula to calculate our test statistic of t, and we can use the information in the problem in which to calculate this value. So we can find our hypothesized value, and this is going to be 100 kilograms. This is based on our problem. We can find our sample size here of 6. Now, we're not given the mean or the standard deviation for this particular problem, but we've got our data, and we can calculate this as we need to, as we're now comfortable calculating the central tendency and dispersion of our data based on previous lectures. Sometimes you may be given this value, sometimes you may be expected to calculate it. So we can calculate the mean, calculate the standard deviation, and this then in turn allows us to calculate that t-value. Same basic structure of calculating the chi-square value, just a different formula. We're then going to take this value and compare it to our critical value based on the degrees of freedom and our significance level. So first we need to calculate our degrees of freedom, n-1, so we have 6 dolphins, so our degrees of freedom will be 5. We then need to determine if we have a one-tailed or a two-tailed test. As we've talked about, our alternative hypothesis is that the mean is greater than 100, so this would indicate a one-tailed test. We're only interested in the right side of the curve. And our significance level is going to be 0.05. So we then find where these values intersect, and this is going to be our critical value. We'll then compare our test statistic, t, to this critical value. And again, if our test statistic is less than our critical value, then we're going to fail to reject the null hypothesis. There's not enough evidence to support a difference with the mean and the hypothesized value. If the test statistic is greater than that critical value, then we can reject that null hypothesis. There is some type of a difference based on the data that we've collected in our sample. In this particular case, our test statistic is greater than that critical value, and so we can infer that the dolphins in our population are heavier than that 100 pounds than we would have hypothesized. Now, we've only gone out and sampled 6 dolphins, and so maybe we get asked the question, well, what if we went out and sampled another 6 dolphins or more dolphins? What would be the actual inference that we would draw then? And this t-test answers the question for us. So if our findings are significant, if we can reject the null hypothesis, the t-test is indicating to us if we went out and sampled another 6 dolphins, we're likely to find the same result. Now granted, if you continued to conduct sampling, you might see some differences here, but the crux of these statistical tests is we're only collecting one sample, but if we're finding a significant difference, if we are rejecting the null hypothesis, it's indicating to us that if we continue to go out and repeatedly sample, we'd find that there is a difference between the mean of and what we are. If we were to make some adjustments to our sampling, maybe rather than going out and only sampling 6 dolphins, we actually sample 20 dolphins, but we're still interested in the same question. Are dolphins heavier than 100 kilograms? We could use the new information to test this in the same way that we did previously, so we can get some more practice using the single sample t-test. So same question as before, does our mean equal 100 kilograms as our null hypothesis, and our alternative hypothesis again is that the mean is actually greater than that 100 kilograms. So we've now got a new mean, new sample variance, new sample size, and we can put these into the formula here, noting that our sample mean is a bit closer to 100 than it was before, but our sample size is greater. So let's see what the effects of that is. So we can go through and we can input in our sample mean and our hypothesized value into the formula. In this particular case, we're given the sample size as well as the sample variance. Now, one of the tricks is that the formula uses the standard deviation. So we need to take the square root of our sample variance, which is 12. We can then go through and calculate out our test statistic for t, 3.727, and we can also determine what our degrees of freedom are based on our sample size, and this is 19. We can then go back to our t-test table, and we can then find what our critical value is. So again, we use the degrees of freedom and our significance level for a one-tailed test, because we're only interested if the weight is greater than 100 kilograms. And we then find where these intersect, and we find that yes, the dolphins are significantly different than 100 kilograms. They're heavier than this, based on our test statistic of t being greater than our critical value. Now, let's look at one last example here for this single t-test. So let's say that we're interested in looking at the weight of oysters in Galveston Bay. We know that across the Gulf of Mexico, on average, they're 500 grams, but we're interested if the oysters in Galveston Bay are different than this. So we've got our data here. We've gone out and collected oysters, and we've weighed each one of them. And we know that our null hypothesis is that the population mean is 500 grams. Now in this particular case, the word problem doesn't indicate if we're interested if the oysters are larger or smaller than that 500 grams. We're only interested if there's a difference. And so our alternative hypothesis is that the mean does not equal that 500 grams. And this is important because we need to be able to distinguish from a word problem what the alternative hypothesis is going to be, because that's going to influence whether we have a one-tailed test or a two-tailed test. And we know that from the word problem, if we're interested in the average values, then we know that we're using a t-test. So again, we're going to start using some of the context clues of the word problem to determine which test we should be using. So we've got our t-test here, we've got the formula for that. We can go and we can calculate the appropriate statistics descriptively for our data. So this is the mean, the standard deviation, we've also got our sample size, and we can input this all into our respective formula. If we're moving too fast for this example, take a moment, pause it, work through it on your own. This will then make sure that it reinforces your ability to use this t-test. We'll also be doing this in class. So now that we've got our t value, we can then go to our t table. We know that our degrees of freedom is small n minus 1, so this is going to be 13. And we know that we want to set our significance level at 0.05. Now, we need to make our decision about which of these columns we want to use. In our particular case, we're just interested if there's a difference between the oysters that we've sampled and the 500 grams that are hypothesized to be the population mean. So in this particular case, we're interested in both the left side of the curve and the right side of the curve. And so this is going to be a two-tailed test. So we go and we find 0.05 in the two tails row. We then find where this value intersects with our degrees of freedom of 13. And this is our critical value for our t-test. Now again, similar to before, we evaluate if our test statistic is greater than or less than our critical value. In this particular case, the test statistic is greater than the critical value, so it would indicate that the sample oysters are different in weight than those 500 grams. In this particular case, it seems to be that they're heavier because the average was 610 grams. Now, for more information on this, I'd strongly suggest checking out section 9.5 in the text, and also working through practice exercises 9.3 to 9.6. The next video is going to focus on two-sample t-tests when we're comparing two sample means to each other.